Okay, so welcome back to our next example of ice tables. It's finding the pH of 1 molar ammonia. Now, the equilibrium constant for ammonia is 1.8 times 10 to the negative fifth. Yes, that looks exactly the same as the equilibrium constant for acetic acid. That might be the universe trying to tell us that common household products are going to be very similar in some ways. Or maybe it's just a coincidence. Probably it's a rounding error. If you took it out to more decimal places, you'd probably find that ammonia and acetic acid aren't quite that similar. And there is a significant difference in that acetic acid is an acid, ammonia is a base. That's a pretty big difference. But anyway, you'll find it does play out very similarly, but there are some important differences that will, I think, be quite instructive. So first we go ahead and we set up our ice table. And here's the first difference, NH3 plus H2O. You have to include H2O in this one because it forms ammonium and hydroxide. Ammonia steals a proton from water. All right. And here is our ice table, ICE. And our next big difference is that we need to include the phases of each of these things. Because when you look at the equilibrium expression, you see NH4 plus times OH minus divided by NH3. Water doesn't show up because it is the pure liquid. And hopefully you recall that pure liquids and solids don't show up in a heterogeneous equilibrium. So we can go ahead and just sort of cross off water here. It's not going to actually show up in the equilibrium expression. It's not going to have any effect in our ice table. We just sort of ignore it. We need to include it in the actual reaction, but we don't include it in the equilibrium. And so, for the next little bit, this problem is going to proceed very similarly to the last problem. 1, 0, 0, then minus x plus x, because it's a 1-to-1-to-1 relationship. So 1 minus x, and x are our equilibrium numbers. And we can assume that the x is going to be negligible when compared to the 1 molar ammonia and cross it off, which gives us an equilibrium expression, KEQ equals x squared over 1 is equal to 1.8 times 10 to the negative fifth, and x equals 0.0042, all the same as before. And then we can go ahead and hop back to the previous slide, and we see I'm even asking for the same sort of answer. What is the pH of 1 molar ammonia? And that's when things start to get a little bit different, because let's hop back over here and look at the reaction. You see that in order to calculate pH, you need H+, but there's no H+ in this reaction. There's just OH-. We will be able to get pH, but it'll take us a few more steps to get there. And that first step looks very similar. It's kind of the mirror. POH is equal to negative log of OH minus, or the negative log of the concentration of OH minus. Okay? And then that means that negative log of 0.0042, so the POH of this solution is 2.38. And you do one last calculation to get the answer. pH is equal to 14 minus POH. So the pH of this solution is 11.62. Once again, we see we're dealing with a weak base, ammonia, and it has even though it's weak, the solution that it makes is still very basic, 11.62. So again, you don't want to play around with ammonia. And that does it for this example. Let's move on to one that slightly different but very similar. So our next problem is a neutralization reaction. What is the pH of a solution of 1 molar, 50 milliliters I should say, of 1 molar acetic acid mixed with 25 milliliters of 1 molar sodium hydroxide? Now, a neutralization reaction means that you get something like this. Acetic acid plus sodium hydroxide produces water and sodium acetate. Remember, acid plus base equals water plus salt, or salt plus water, whatever. Now, the way we work a neutralization problem like this is we neutralize. Now, that means we're going to need to find out how many moles we're dealing with, because we're adding volumes of different liquids together. So we have 50 mils of a 1 molar solution of acetic acid, and we have 25 mils of a 1 molar solution of sodium hydroxide. Yes, I've added decimal places to things. I'm taking the liberty. All right. So what that means is 1 molar is 1 mole per liter of acetic acid times 0.0500 liters. Okay, you need to get the units to match up, which means we have 0.050 moles of our acid. And then a similar calculation is 1 mole per liter times 0.0250 liters equals 0.025 moles of our base. Now, in a neutralization reaction, you neutralize some or all of your acid and base. So we have more acid than base. We're going to have some acid left over. So that's 0.050 moles of acid minus 0.025 moles of base, because you have a monoprotic acid and a monohydroxide base. Okay, it's just 1 to 1. That will leave us with 0.025 moles of acid left over. And this is the important part. For the equilibrium expression, we have 0.025 moles of acetate have been produced. Okay, those are the two numbers we are going to plug into our ice table. But before we can just throw things into the ice table, we need to get it back into terms of molarity. So it's 0.025 moles. It's the same number of moles for each one, so that simplifies things, divided by 0.075 liters. Why? Where? What? Where? What? Well, to neutralize these things, we had to mix them together. So we poured those two solutions together, and 50 mils plus 25 mils is 75 mils, or 0.0750 liters. And then you do that math, and you get a concentration for each of these of 0.33 molar. So now we can set up our ice table. So the equilibrium expression we're looking at is exactly the same as what we saw the last time we worked with acetic acid. The sodium hydroxide we put in there that neutralized some of the acetic acid, it's been completely used up. It's gone. It's not going to show up. It can't do anything else. So all that's left is acetic acid dissociating into H plus and acetate. Okay? That's it. So here's just the outline of our ice table. And the initial concentrations are what we just found. That's what we went to all that trouble to find. That's why we went to all that trouble to find them. So the initial concentrations are 0.33 molar of the acetic acid, 0 molar hydronium, and 0.33 molar acetate. The change in our concentrations are minus X, and plus X. Very straightforward. Now, we know that it's going to do that. It's going to go to the right because there's no hydronium. It can't go to the left. You can't have negative stuff. Okay? And our end concentrations are 0.33 minus X, and 0.33 plus X. Now, here is the $64,000 question. Can we assume any of those X's are negligible? So we take a look at our equilibrium expression. KEQ equals concentration of H plus times the concentration of C2H3O2 minus divided by the concentration of vinegar. This is where it would be really helpful to have awesome algebra intuition, but I'm going to go ahead and tell you that yes, okay, you can make X negligible. 0.33 is a pretty big number relative to 1.8 times 10 to the negative fifth. So you're going to have to multiply by a very small number in order to get 0.33 down to 1.8 times 10 to the negative fifth. Okay, so X is going to be a very small number. So that means that 0.33 minus x, that x is negligible. And then we have our other, sort of a bonus, 0.33 plus x. That x is also negligible. So, when you go ahead and plug these new numbers in, you get 1.8 times 10 to the negative fifth is equal to x times 0.33 divided by 0.33. And then, of course, 0.33 divided by 0.33 is just 1, so those cancel out. And that means that x is equal to 1.8 times 10 to the negative fifth. Now, let's just be careful. Let's double check. Is 1.8 times 10 to the negative fifth negligible compared to 0.33? Well, 0.33 minus 0.000018, yeah, that's negligible. It's going to disappear into the rounding errors. Okay, so boom. Awesome. Wonderful. Great. Good. Let's go ahead and answer the question we were asked. What is the pH of this solution? pH is equal to negative log of H plus. So it's the negative log of 1.8 times 10 to the negative fifth. The pH of this solution is 4.74. And there we have found our answer. Yay! And now, before we wrap it up for this chapter, I would like to go ahead and ask, how can you determine if x is negligible? When do you get to say that it's negligible? Even if you double check, right? Because, you can't always just write it off as a rounding error, right? 5%. 5% is a good rule of thumb for when it's okay to sort of ignore x. Okay? So if you make the assumption that x is negligible, and you go through and you do the work, you find x. If x is less than 5% of whatever you were comparing it to, then yes, x was negligible. If x is greater than 5%, then that's just a little bit too big, and you're going to have to go through and you're going to have to do all of the algebra that is required. Okay? So that's the rule, okay? 5%. Another good rule of thumb is just look at the equilibrium constant. If you have a really tiny equilibrium constant and you're going to the right, then you're not going to have to worry about it. So long as you have a significant amount of stuff there on the left to start with. If you have a huge equilibrium constant and you're moving to the left, then you probably don't have to worry about it. Anything in the middle, maybe you're going to have to be careful. And if you have really small quantities of stuff, then you're going to have to just suck it up and do the algebra. But that is the rule for that, and that's where we're going to leave it for Chapter 13. Now that we've talked about equilibria, I'm going to go back and do a little addendum, tie this back into Chapter 12, so we can get a better, fuller understanding of reaction mechanisms and how they can tie into our rate law.